Okay. Hello, everybody. Nice to meet you. I am Michele, and I'm very happy to be here today. And I'm thankful to the organizers for inviting me to give this series of lectures at this school. It's an honor and a big pleasure to be here. Before I start, let me mention a couple of references. There are many lecture notes. Many lecture notes on the topic. Some that are useful, that I found useful, but I might not cover, are these notes by McGreevy on generalized symmetries in condensed matters. And then there are notes by Shafernameki, ICTP, Gomez has a nice introduction to 303. Shao, I think I mentioned Shao, we will follow some aspects. It has some TASI lecture notes from last year. Brennan, and also, hello, and there are also some Simon's lectures from past November, which we will follow in some extent. But most of what I will discuss today is based on conversations with Kantaro Omori. In fact, I owe to Kantaro a lot of what I know about generalized symmetries, and you can find some aspects of what I will discuss today in our papers and also in papers to appear. I'm not sure I will follow a conventional approach for this lecture series, precisely because there is a lot of already published sets of lecture notes that cover some more orthodox type of approach to generalized symmetries. So I designed a course which will touch upon various key features, and I hope it will be useful. So symmetries have a key role in our understanding of quantum field theories, no? If I write too small or too little, or if you don't understand what I write, you can interrupt me and ask me about it. My handwriting will become worse and worse as the lecture goes along and as the course progresses. And I assume most of you have been already exposed to this idea. Many of you probably have already followed a course in QFT, and you are already familiar with the distinction between what are global symmetries versus gauge symmetries. No, is it a correct assumption? You're all familiar with this? Yes? Okay. So you won't jump on your chair when I say that gauge symmetries are not symmetries. No? They are a redundancy. They're a redundancy, they don't act on anything, they don't transform anything at all. No? They are just a useful, very useful tool to write down local Lagrangians for interacting quantum fields. No? They're very useful though, very useful. No? Interacting local Lagrangians. And we will try to refer to them as gauge redundancies. No? There's a better name. Global symmetries, on the contrary, they act on stuff. Or they act on states, they act on operators. There is a lot of information about your theory once you understand how to read off its symmetries, the operator of the quantum field transforming representations of the symmetry, no? But I assume you know about it, no? Is it correct assumptions? Stop me if you don't, no? You probably have heard about Ward-Takahashi identities. The idea is that whenever you have a symmetry, you consider your correlators, and there are relations between different types of correlators, no? And these relations are encoded in Ward-Takahashi identities. We'll see many of them in the course, so I won't waste time giving you a version of Ward-Takahashi identity that you probably have already heard about. We will see how to get there from a slightly different perspective. And probably you also have been exposed about various basic features of global symmetries, such as foundational important features like the Coleman-Mandula theorem. Is that true? Is that false? Raise your hands if it's false. Okay, 3 hands. 3 hands is already enough for a little parenthesis. So Coleman-Mandula theorem is a I mean, in the 70s, people have studied quantum field theories because they were interested essentially in extracting their S matrices. No, they were developing quantum field theory to study scattering experiments. And if you study the S matrix as an abstract object, you can consider its properties. You can ask, what happens if my field theory has higher spin currents and an S matrix? No? And Coleman and Mandula asked themselves this question: what is the most general symmetry that a quantum field theory with an S matrix can have? No? And for instance, they found out that if you have a theory with higher spin currents, the S matrix must be trivial. It must be a free theory. No? And then I think Zhiboyedov and Maldacena proved it also for conformal field theory, that if you have a conformal field theory with higher conserved spin currents, then also in that case the S matrix, it must be a free theory. No? It doesn't have an S matrix, but it must be a free theory. So there are structural features of interacting field theories. No? And this statement about Coleman-Mandula is an example. No? It's a what is the most general type of symmetry structures you can have? No, it's the Poincaré group and then some internal symmetry transformation. No, essentially, which is local, not higher spin. No. So my main interest in symmetries. No. So this is it for this. If you want more, we can discuss afterwards. If this was not enough of a reminder, my main interest in symmetries. For me, but also for the community, I think it's not, comes from their interplay with RG flow. So you have an ultraviolet theory, you have an RG flow, and you have an infrared theory, and you have a symmetry that acts, a global symmetry that acts on the ultraviolet theory, and you have a global symmetry that acts on the infrared theory, no? And if you have an RG flow that relates your field theory in the ultraviolet with the field theory in the infrared, then the RG flow establishes a map, say. Let's call it phi RG. From the ultraviolet symmetry to the infrared symmetry, no? Are you familiar with the RG flow? Do you have you been exposed to it? I assume that's correct, no? So you know, like probably you have seen this type of behavior, no? So first of all, what are the properties of this map? In these cases, in the context of this introduction, these are the symmetry groups, no? They act on your theory. And this is a map between groups, no, which preserves the group structure. So it's phi RG is a group homomorphism, which just means that it is a map of groups that is compatible with the group structure. Okay, so it maps products to product and identity to identity, so on and so forth. What other features we know about this group homomorphism? No, so you see, like it's not a surjective homomorphism. What does it mean that that it is not surjective? No, your professor of linear algebra is crawling from under the his back. What does it mean that it is not surjective? No. Um, come on. It can be, this one can be larger, no? That's correct, no? And it is not injective. Does it mean that it is not injective? No, injective means that it maps the identity to the identity. Say it doesn't have a kernel. No, so the idea is that in the infrared here, no, along the RG flow, it can happen that you start dropping higher order interaction terms. No, there are some couplings that along the RG flow they flow to zero. No, and so what happens is that in the infrared, this theory can have emergent symmetry. No? And as far as the fact that it is not surjective, what can happen is indeed that along the RG flow, it can happen that you start integrating out massive states. No, there are things that decouple. In your infrared description, there are certain things that along the RG flow develops a mass, and the mass is very big compared to the scale of the infrared, and so you can neglect those particles, no? And therefore, some part of this symmetry might not act anymore in the infrared, no? There is stuff that decouples, no? This is stuff that decouples, no? No? And instead, the fact that it emerges means that along the RG flow, no, some couplings that were preventing a given symmetry might flow to zero, no, and then you have more symmetry in the infrared than you had in the UV, no. So this group homomorphism is interesting. Okay, it's not like it's not just okay. You have the symmetry in the UV and the same symmetry in the IR. That's it. No. There is a lot of dynamics here. No, so this group homomorphism is interesting. No, is interesting. There is dynamics that goes on. No, and yes, and for this reason we want to study it. We want to understand it. We want to understand how to constrain it. No, want to compute. We want to understand what are emergent symmetries and how do they come about and how do they develop, no? And there are two main applications that we might have in mind, no? Two applications. UV to the IR application, which is that you start from your microscopic model and use the symmetry to constrain what happens in the macroscopic, no? Which is essentially what we do whenever we do particle theory, no? And then there is an IR to UV, no? Which is given some macroscopic phenomenon. You want to use symmetry to infer possible macroscopic origin. Microscopic origin. No, so two applications going from the ultraviolet to the IR. We start from some microscopic model, and we try to use symmetry to constrain what happens in the macroscopic. And then there is an infrared to the UV, given some macroscopic phenomenon. We want to use the symmetry to infer some possible microscopic origin of it. No, so this is, if you like, you have the spectrum of hadrons, and you want to find the QCD Lagrangian. No, this would be an infrared to the UV. No, you know what is the spectrum of excitation in the infrared. You want to understand what is the ultraviolet microscopical physics that determines and explains that. No, so more or less this is the reason why symmetries have a key role in our understanding of quantum field theory, because the name of the game in quantum field theory is exactly this: relations between the microscopic and the macroscopic. That's the question in quantum field theory. No, like really, like it is transversal to all possible applications of quantum field theory, from condensed matter to statistical physics to particle physics. No, so well, what do we know about symmetries? There is a fundamental principle that we will use throughout these lectures as a pathway to symmetry, and this is the locality principle. No? We will use it, we will encounter it a lot during the course, and we'll use it over and over and over. So, if you like, this is the defining characteristics of QFT symmetries. Is that they preserve locality. What does it mean that they preserve locality? No? So naively, we think, if you think about what we know about symmetries in our textbook course, we have our quantum field. No, I use a collective letter phi for any fields, like this is any fields. No, we have our quantum field, and we have a symmetry transformation. No, and the fact that it is local is just the fact that it is a local function of the fields. No, that relies solely on the local value of the field and of its derivative. No, relies. Okay. Naive characterization of locality. No? So the transformation of the fields. No? When you have seen many examples of this type. No? When x prime is different from x here is a point in space-time. Then you speak about space-time symmetries. And when x prime is equal to x, you speak of internal symmetries. No? And be careful, there is be careful. Sometimes in textbooks, gauge redundancies are referred to as local symmetries, but this is not what we mean here, no? Okay, so please don't make confusion, okay? Yes? Something that does not preserve locality. Well, something that acts in a way which is not related to the insertion of the field at a point in space-time, no, something that transforms everything, say, no? Mm-hmm. Mm-hmm. It's tricky. It's very tricky, and we will see immediately how tricky it can be. No, so this definition here is very naive. No, so it's not a good. I don't think it's a good characterization of locality. No, but it's just a naive way of thinking about it. And essentially, many of the textbook examples of symmetries that you have encountered so far are of this type. No, they preserve locality in this sense. No. But not all locality preserving symmetries have this form, no? So let's label it star, no? So not all, so most, well, all maybe, all textbook example of symmetry, let's say, all textbooks have, most, most textbook example have the form star, no? But not all locality preserving symmetries have such an expression. No? So star is what we can refer to as a classical symmetry. No? It's the form of a classical symmetry of the field, something that you would encounter when you study the Noether theorem, for instance. No? It's a property that you can study. I don't know. You take your field, you take a symmetry transformation of that form, no, leaves the Lagrangian invariant. You deduce that it has that symmetry. It's a symmetry at the classical level, no. But there are other types of symmetries which in the literature go under the name of quantum symmetries. Or topological symmetries. No? And probably you have encountered also this. No? For instance, examples of this arise whenever there are quantum numbers associated to topologically non-trivial field configurations. No? For example, you can think about the winding symmetry of a compact boson. Or you can think about the monopole symmetry in 2+1 dimensional abelian gauge theories. No? Those are examples. So you take your quantum field, you take your field theory, you study it, find out that there are some field configurations that have a finite energy, no? That are not, they don't arise as perturbative excitations of the field. They are something that people call solitons sometimes, no? And they are protected, but they are protected by some different kinds of quantum numbers. They are protected by the fact that they are field configurations that have a non-trivial topology in field space. And this non-trivial topology is what prevents them from decaying, no? Like a monopole has a non-trivial topology, a magnetic charge, no? And in 3 dimensions, monopoles are like point operators, and so they have a symmetry, and this symmetry is something topological, something more quantum, no? It does not appear like this naively in your Lagrangian, no? It's an example of a Chern-Weil charge, no? No? So I don't know how many have you ever been exposed to this in your experience with field theory so far? Some of you, yes. How many? Higher. Okay, so there is a lot of people that haven't seen this yet, no? So for those of you that haven't seen it yet, don't worry, we will encounter them in the course. And for those of you that have already seen it, don't worry, we won't speak about them at any level of detail. So you won't get bored, no? But we will touch upon it, no? But this is essentially to stress that, okay, so there are these classical symmetries, and there are these other ones that are related to more quantum features of the field, no? These topological configurations, these solitonic degrees of freedom, well, not really, solitonic excitations, let's say, solitonic excitations of your quantum field, no? However, in many instances, it can happen that these quantum symmetries, these topological symmetries, are mapped to classical symmetries. No? So it can happen. So for a long time in the literature, people when they were encountering these quantum symmetries and topological symmetries, they would say that they were non-local, no? Because they didn't act like that naively, no? But then we learned that field theory, well, they learned, we learned from them. They learned that this was just an artifact, no? Because topological and quantum symmetries can map to classical symmetries under duality. No? Something magnetic in a duality frame becomes something electric in a different frame. No? And so something that look at very quantum, very topological, very, very mysterious, becomes something very classical. It's just a matter of the duality frame at which you are looking your theory. And so because of duality, well, first of all, this distinction is not fundamental, no? And second, also these topological quantum symmetries are locality preserving. No? And so, from a contemporary standpoint, we would like to have a universal way of characterizing locality preserving symmetries. No? Like what we know, the formalism that we know so far, no, has these features that are somehow tied to a perturbative formulation of quantum field theory. No? And however, like while it is very useful, no, because we can compute. If you have a perturbation expansion, you can compute. No, so it's very useful. It kind of hides some features, no, like the fact that certain things seem to be a very different phenomenon, and instead they are literally the same phenomenon. And so, from a contemporary standpoint, a universal characterization of locality preserving symmetries is given in terms of topological operators. Where can I write it? I can write it here. No? So, what are topological operators? Topological operators are extended operators in the quantum field, in your quantum field theory. By extended, I mean that they are defined over submanifolds of spacetime. No? And they are topological because they can be deformed and displaced. No? At no cost. There is no energy cost in wiggling these topological operators. No? And the correlators that include them, no? Where can I write above? No? Correlators that include them correlators that include topological operators remain invariant under smooth deformations of their support. Okay. So this means, you see, you have your correlators, no? You have your operators inserted at various points, no? Something like this. And you have your topological defect, some sort of, oops, sorry, which squeaks, no? Some blob like this, no? And let's call it D for defects, no? And you can wiggle it as much as you want, no? This like amoeba-like configuration, no? Blah, no? And as long as it doesn't intersect the insertion of the other operators, the correlator stays unaffected. The value of the correlator stays unaffected. No? So correlators that include topological operator remain invariant are the smooth deformation of their support. No? And here, like you should think about this guy, this topological defect, the topological operator, is being supported on a submanifold. No, it's not inserted at a point. It's an extended operator. No, it's like supported on a sphere, supported on. It has some. It's like a membrane, if you like. It's a topological membrane that you can wiggle and move around, push, and at no energy cost. The correlator stay invariant if you just move it around, as long as it doesn't touch the point where operators are inserted. Yes. Oh yes, yes. You can move it away. No, in this case, no, no. As long as it doesn't touch the other ones, it just has no effect whatsoever. No, but the interesting things start happening when this operator starts intersecting with the other one. No, if it can. Um, if it can cross or it can link with other operator insertions, then when you deform it, the deformation is no longer smooth. No, it can pinch, and whenever that happens, there is some interesting action going on. No, and it is this action that generalizes the action of symmetries on the quantum fields that we were after. No. So whenever you see this probably you've seen talks about this topic in I'm not sure, but often people draw diagrams like this. They would say that symmetries is the same as topological operators, no? No? And this remark, I think, I learned it from the Bible on the subject, which is this paper by Gaiotto, Kapustin, Seiberg, and Willett. It was 14 or no, and but I think you should think about this double arrow as the right hand side defining the left hand side. Okay. The right hand side is the definition of the left hand side. If you are interested in symmetries that are locality preserving, no? Now, we will explicitly verify that this correspondence reproduces known symmetries in the case of a scalar field. No? We'll do it along the course. No? The way in which we will do it will be very unconventional. So we will will exploit the fact that we can write topological operators exploiting locality, where the notion of locality that we are going to use is the fact that we can, if you have a quantum field theory which is local, defined on a Euclidean space-time, you can start cutting the space-time into parts, no? And you can go on as much as you want, and all the time this operation of cutting and pasting the space-time must be consistent, no? And so that's what we mean by locality preserving, the fact that we can always cut space-time and obtain a consistent representations in the path integral. We can cut it with topological defects. And then we will see how, from this perspective, we can recover what we know about ordinary symmetries. Okay, this is a bit unconventional, but I think it is instructive. And well, before we go on, I mean, I think probably that's something that we'll do next. I'm not sure if it is going to be next time or on Thursday, because this philosophy. This philosophy, well, this is essentially the mantra of the subject, no? So everybody's repeat something that everybody repeats, no? Until, but this mantra was very well developed and well studied in the context of two-dimensional conformal field theories, no? Where there is a very well developed theory. Very well developed. And so my plan is that tomorrow we will go over this idea in this context. No, we have 4 hours, so it should be enough. But before, I need to gauge a little bit the audience. How many of you have been exposed to two-dimensional CFTs before, by raise of hand? Wow. Yeah. Very good. So Virasoro is a friend? Yes, kind of a friend. Modularity constraints, are they friends? Not much, okay. And how many of you have encountered a twisted Hilbert space? Okay, good. So now more or less I know how to gauge the starting point of my lecture tomorrow. Okay, very good. So this is what we will explore tomorrow. And in that context, we will just have topological defect lines. As symmetry generators. And then we will move on to higher dimensional field theory. No? A lot of things that people do in the context of generalized symmetry is taking aspects of the theory of topological defect lines that are well known and well developed in 2 dimensions, and think about how to generalize them in higher dimensions. No? So we'll see some features here that we will try to generalize in higher dimensions. No? And in higher dimensions, however, so in 2 dimensions, we have very little to play with. No? There is not much space. But in higher dimensions, instead, it is convenient to label the operators by their codimensions. No? So in D greater than 2, it is convenient to label the topological operators by their codimension. And so people would start speaking about p-form symmetries. No? P-form symmetry from this perspective would be a topological operator of codimension P plus 1. No? Do you remember what is the codimension? Yes, you're all familiar with it? Okay. In particular, well, zero-form symmetries are what are codimension 1 and are the ordinary symmetries would fit in this class. No? There are also things that are called -1 form symmetries, and you can think of them as if they are space-filling topological defects. Space-time filling. That acts on couplings as a slogan, but I'm not sure we will have time to touch upon them, maybe, but just want to bring them up because they are important, they have important applications. And as we mentioned, these topological operators have an action. No? We will see many examples. An action. No? So for ordinary symmetries, we have an action by measuring the charge. No? It's like the Gauss law. You insert an operator labeled by a group element. No? G is an element of your group. You have an action by linking. Essentially says that this is equivalent to having an action of the representation on the operator inserted at the same point, just by linking. No? Point and spheres of codimension 1 link, no? in space-time. And this action, however, can be used to give conserved quantum numbers. This linking action can be used to give conserved quantum numbers to lines and to extended operators. No? Like if you insert an operator along a line, you can have a symmetry. Now is on a sphere of codimension 2. No? Again, labeled by an element of G. No? And so this is the so-called linking action. But topological operators can also have an action by crossing. No? So you can insert a given operator, no? on a given surface, say sigma d -1, and you take your line, and the line crosses the surface and comes out transformed. No? Again, like this. No? So this is a crossing action. No? What? This is a representation, sorry. A representation. No? So your symmetry defect will act, if they are labeled by a group, they will act on your operators and they will transform them in linear representations. No? If the operators are local, they will transform in linear representations. No? And similarly, if this is what happens when you do this linking action. No? The crossing action is more interesting. We will see that the crossing action is slightly more interesting. No? So in this case, the representation can become projective. No? Instead, here it is linear. So there is an interplay between crossing actions and anomalies that we will discuss. No? And what I want to remark at this point is just that you see these topological defects, they give rise to a language, a formalism, that can give quantum numbers to extended operators. No? The slogan is that we get quantum numbers for extended operators. No? And so in particular, you immediately see that there are some features here in the structure of these actions. No? So for instance, the fact that the topological defects that act on point have codimension 1 means that these groups here, these would be the zero form symmetry groups, they can be non-abelian, no? Because if we insert another defect, maybe I should use a different color. Do you see, if I write it in green, do you see it? If you insert another defect, the color is the same. If I insert another defect, no? Say UG prime on SD minus 1, there is clearly an ordering. No? There is one that comes before the other. No? But in this context here, the one that acts on line, you see, like, there is not a real ordering. We can take this, move it out, move it in. No? The configuration space is the transverse direction. No? If they are codimension 1, the transverse direction is a point. If they are codimension 2, the transverse direction is a plane. No? It's a plane. No? So the configuration space of codimension 2 defects is that of points on a plane, and so there is not an ordering. Instead, the configuration space of codimension 1 defects is a line, and so there is an ordering. No? And so you see that, for instance, these P4 zero form symmetries can be non-abelian. But P-form symmetries, which acts by linking, are typically abelian. No? Hey, good question. No, I was a bit quick, but the idea is that you see, if you insert an object of codimension 1, no, it means that it leaves out of space just one direction. No? And you can consider the direction to be the direction which is normal to its word volume, say, no? Where the word volume is like the surface of this sphere, no? And now, if there is a normal direction, if there is only one normal direction, no, you can use that to say which defect is inserted before, no? If it is codimension 1, you can introduce an ordering because there is only one normal direction, no? And so you can say which one comes first. But if it is of higher codimension, if it is codimension 2, then there are two normal directions, and the configuration space of a topological defect, which is of codimension 2, is a plane. It's a point in a plane. And there is not an ordering for points on a plane, no? So if you just have genuine codimension 2 defects, and they are labeled by elements of a group, that group better be abelian. Okay? Yes? Yes, exactly. You can, if you start combining them, no, if they start intersecting one another, acting one on another, crossing, no, then they can start giving rise to some more interesting structure, no, and indeed, like in a sense, string theorists already knew about this structure, no. When we study string theory, we study membranes. And membranes are source for higher dimensional gauge fields, no? And the structure of membranes can intersect, they can end on one another, no? The main difference is that in string theory, when we encounter these higher symmetries, they are gauged. So they are not really symmetries, no? They are higher gauge fields, the Ramond-Ramond fields in string theory, no? And instead, in field theory, it can happen that you encounter these structures, but as part of the symmetry of the field theory. So they are global symmetry. They really act on things. They act on line operators, etc. And so from this perspective, it is interesting. As far as you remember, when we started this lecture, we spoke about this homomorphism between the symmetries in the UV and the symmetries in the IR. No? When we thought about it the first time, today, we had in mind groups and homomorphisms of groups. No? But now, well, now we have these topological defects. No? And they are what we want to use to incorporate symmetries in our formalism. No? And then there is a question. Do we have an RG morphism also in this case? And what is a morphism of? No? What structure am I mapping from the UV to the infrared? No? What is the structure that organizes these topological defects? No? And the idea is that there is a structure, and the structure is that of a thing that can be scary at the first time, but I hope eventually I will convince you it is not. No? So we have a symmetry category. There is a symmetry category in the UV. There is a symmetry category in the infrared. And there is a proper notion of an RG morphism from the one of the UV to the one of the infrared that has the same kind of features. No? The only thing is that now it's not something that maps a group into another group. It's something that maps a symmetry category into another symmetry category. No? And our aim in this course is to expose some of the features of this. So in particular, what I want you to remember is that there is a lot more structure. There is a lot more structure. No? To illustrate how much more structure there is, how do you think about a group in terms of categories? No? What is a category? No? Categories are a collection of objects, in a sense, and collection of morphisms. No? Objects and morphism. Morphisms are just maps between the objects. Okay? So you see, a group is a category that has only one object and whose morphisms are all invertible. Okay? Only one object. And the morphisms are all invertible. There is always there is one object and there is a group element. For every group element there is an inverse, no? And the inverse composed with the group element is the identity. You know, this is a defining feature of group multiplication. There is always an inverse, no? And so there is only one object and the morphisms are all invertible, no? And so, like, in general, a symmetry category has many objects, no? And the morphism can end up being non-invertible, no? So there is a lot more structure, but still there is a notion of a morphism, no? And there is an interesting question that we can ask. There is a question about what happens to the topological defects of the UV theory with respect to the one of the infrared theory. And hopefully at the end of the course, we will see that this structure is something we can exploit to learn something more about the RG flow. Okay, yes? If you think about describing a group as a category, it is a category with only one object and whose morphisms are all invertible. No? The group, the elements in the group, no? They are the morphism in your category. Okay? And the object is just one object on which they act, like, I don't know, can be a vector space, for instance, no? If you want a representation of this category, no? But it's just one object, no? Exactly, yes, that would be a representation of the group, though. So as an abstract gadget, you can also look at it in terms of generators and relations, say, and that's it, yes. Oh, yes. Well, yes, like the idea is that I will try. I don't know if I will succeed. But there is a distinction, no? There are the topological defects and there are extended operators on which the topological defect act, no? And so when I was I try to distinguish them using colors here. So the white dot and the white line, they would be defects that are non-topological, like a Wilson line, for instance. But we will see examples, no? So in quantum field theory, you can have extended defects. You can have you can insert lines, you can insert surfaces, no? And we will see even in Maxwell theory there are lines that you can play with, and they are charged with respect to higher symmetries, no? So we'll play with it. And in this context, yes, in the context of this introduction, you can think of this as just a Wilson line, for instance, no? But in general, gamma can be any submanifold. It's just that in a correlator with a non-topological defect insertion will depend on where it is inserted, no? So there is a distinction, no? The symmetries are associated to topological extended operators, and the operators that are charged with respect to the topological ones would be also extended, no? And if you have a p-form symmetry, that would naturally act by linking on an extended defect which is inserted on a p-dimensional submanifold, no? Does it make sense? Am I too? Okay. Yes. 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 Maybe this is a good moment for a short break. Is it okay? We resume in how long do you need? 10 minutes? Is it okay? Yes. Are there more questions? Eh? Well, because it is something that maps a category into another category, and so that's the definition of a functor. Yes. I'm not assuming anything about it. Yes, we don't know. In fact, we already know that it's probably not going to be. No. Yes. Hmm? So from the question that I got during the break, from some questions that I got during the break, I realized that I was a bit too quick in this introductory sketch. No. So you see, when I say so the reason we care about this, no, this p-form symmetries, etc. No. So when I say that they give rise to quantum numbers for extended operators, no? This is related to a question that we got about this W, no? So the idea is that no? When you measure the charge of a point operator, no? You do it by inserting your operator, no? At a point x, and by considering, no? Measuring its charge on a sphere that contains it, no? So there is a notion, there is a sense in which we can say whether this point is inside or outside this sphere. No? Think about the Gauss law. No? You measure the charge of an electron by surrounding it with a sphere, and you measure it. No? Now, what we are after, no, is something that can be used to give rise to a charge of an operator that is no longer inserted at a point, but is inserted along a submanifold of our space-time. No? An example that we will see later in the course, for instance, in Maxwell theory, would be a Wilson line. No? So it's a holonomy of your Wilson loop, a holonomy of your gauge field. No? it's inserted along a line, no, and it's you take your gauge connection, no, and its support is just the line over which it is inserted, no. We'll go over these operators at length, no. But now, like what you are after is something that can say whether the line is inside or outside of it, no. So a sphere of codimension 2, no, can say whether the line is inside or inside of it, no. You can if the choice of the codimension, no, is so that you can speak about the interior and the exterior, and you can say whether this line is contained inside this sphere or not, no, is linked or not by this sphere, no. How do you understand whether something is linked by something else? The idea is that you fill it in, no, you fill it in, and you see whether it intersects, no. So you fill in, and now it intersects, no. And so when I speak about a linking action, no, what I mean is literally the fact that, for instance, now let's think about a three-dimensional space, no. You have your Wilson line operator, and you can link it with another curve, no, in 3 dimensions. Curves link, because if I have a closed curve and I fill it in, then it gives rise to a surface, and a surface will intersect a line. Okay? So the idea is that a p-form symmetry, no, is a topological operator of codimension p plus 1. No? What does it mean? It means that there are p plus 1 normal directions of empty space that are not on the word volume of the topological defect. No? And so it can link with something that occupies p dimensions. So a p-form symmetry measure the generalized charges, if you like, of an extended defect that has a word volume of dimension p. Okay? So when you look at this table, we are defining the topological defects. They are the symmetry generators, no? But in order for your symmetry to do something interesting, it must act on something else, no? And this topological defect will have actions on extended operators. And the extended operators will have supports of their own, which have a given dimensionality. Okay? Does this help clarifying a little bit this picture? No? No, don't worry, like this is just a sketch, and in the following lectures we will go over explicit examples of field theories with where we will construct explicitly these operators and the corresponding topological defects and their actions. Okay. Okay. And now, to conclude today's lecture, I wanted to give a little bit of an heuristic picture of what type of structure we expect on those symmetry categories. Okay? So, and please interrupt me with questions if there is something that you don't understand or something that you want a clarification about. Do it while we go, because it's helpful also for everybody else. No? So heuristics. No? So yeah, we have about half an hour. No, I think it's a good topic. So the main reason why we expect to have categorical symmetries has to do with the fact that in nature, symmetries are emergent. So, so in any theory of nature, global symmetries must be emergent. No, meaning that they hold only below a given energy scale. Lambda, where lambda is moreover smaller than the Planck scale. So, do you agree with this claim? Bah. So there are many different ways to convince ourselves that this must be the case. Okay, many different proofs. And the one that I will report here is an argument that I learned from a paper by Banks and Zyberg. And more specifically, the argument is in a paper by Cordova, Omori, and Rudilius. The archive is 2202. So there are arguments based on holography. There is a paper by Harlow and Oguri, which is very interesting about this. But we want a more hands-on, lowbrow argument, which is based on the physics of black hole. No, so black hole physics. So the idea is that we want to use what we know about black holes to argue for this claim. Okay, it's our claim. And then, building on this claim, we will argue that symmetries must be organized using a higher category. And the main point is that if you have a theory of nature, this theory of nature must include gravity, and so it must include black holes, no? So consider a gravitational theory, take a gravitational theory, and assume it has a U1 conserved global current. Okay. And assume also that there is a free scalar that has a charge Q under such U1 global charge, okay? Otherwise, it is free. Now, if we start condensing a large number of phi particles, no, in a very small region of space-time, then the density of the system can be increased enough to form a black hole. No? This is a fundamental theory of nature, so there is gravity. So if you start piling up condensates, at a certain point the density will be so high that it will form a black hole. Okay, so condensing phi particles can form a black hole. Now, the black hole, if we have a number of n of these guys, the black hole will have a charge which is order nq. Okay. What we are after is our claim, no? So we want to rule the fact that we want to prove this, no? So one feature of black holes, I don't know, we have lectures on gravity. I don't know if they will cover features of black hole, but one key feature of black holes is that they evaporate. Okay, so black holes evaporate. It's a phenomenon due to Hawking. No, the idea is that black holes have horizons, and sometimes they can pair produce particles near the black hole horizon in such a way that of the particle-antiparticle pair that is produced, one particle escapes and one particle fall in the black hole. No? And so by this effect, they start losing energy. Okay, they lose energy. No? And they start becoming smaller and smaller. No? Now, this Hawking evaporation, no, is a semi-classical effect. It requires the black hole to be of considerable size, no, so that this quantum ripple of the field can fall one part in the black hole and the other outside of it. No? And so, like this Hawking evaporation stops when the black hole becomes small, no? Of order the Planck length. No, when quantum gravitational effect become important. No? So when that happens, no, we are left with a very tiny black hole of charge nq, because this pair production is by definition neutral, and so the black hole will not lose charge by Hawking evaporation. No? So you end up with a very tiny black hole of size the Planck length, something like 10 to the minus 35 meters, no? Like very tiny, no? Of charge nq. No? And we can do this as much as we want. No? It's a theory that has this free scalar. We can just start condensing again and construct another one of these tiny black holes of charge nq. No? And go on and on and on, no? Until we get a whole bunch of them, no? A lot of them. A lot of these tiny black holes, no? They don't decay, no? Because they have this global charge that prevents them from decaying, no? And not only they don't decay, they also don't interact with one another, because this is a global charge. It's not a gauge charge. They are made out of these free scalar fields. They don't talk one another, no? And so eventually you go on and pile up these black holes. You end up with a black hole that has a size which is as big as you want, no? A collection of these Planck's with an area as big as we want. No? However, this ends up clashing with another feature of black hole physics, which is the Bekenstein-Hawking entropy formula. Bekenstein-Hawking says that the entropy of a black hole it goes like a quarter of the area of the black hole. The area of the black hole horizon, no? So the entropy is literally the number of microstates, the logarithm, no, of the number of microstates. And this is the classical area of the black hole. You just measure the area of the horizon, no? At the horizon. You see, these things, these tiny black hole that have a size length of the length of Planck, no? Planck length, they don't interact one another, and so they form a single macrostate, no? They form a single macrostate. No? They don't have a number of microstates which is such as it increases at will, like the area of this configuration, because we can collapse them, and as many as we want, we can collapse them. And so you see, we reach a contradiction. No? We reach a contradiction because we can increase the area of this black hole as much as we want, but it has a single giant macrostate, no? With no interaction whatsoever. So it's a violation of this formula. And this formula is a crucial feature of the quantum dynamics of black holes, of the thermodynamics of black holes. So it cannot be contradicted by this experiment. No? So yes. That's a good point. But they will not form, because of that, they will form a single macrostate. They will not have the intricate structure to give rise to as many microstates as you desire. It's a free scalar. And so there is a way out to this, which is that the symmetry is violated before the Hawking evaporation stops. So the Hawking evaporation stops when the black hole becomes so small that it is of Planck's size. No? And if the symmetry is broken before that happens, then the black hole will be free to evaporate completely before it reaches the Planck size. No? And so, in order to avoid a contradiction with the entropic properties of black holes, we can assume that symmetries are violated. No? If this is the Planck size, when the Planck scale where the Hawking evaporation stops, there is a scale below it where symmetries are broken, are violated. And for this reason, we expect symmetries to be emergent. In gravitational theories, we don't expect there are any global symmetries, but while we decouple gravity, while we go below the Planck mass, no, at scales where gravity decouples, when field theory descriptions emerge, also symmetries emerge. So there could be another way out, right? Because then the black holes, they're replaced, not necessarily right. So there is another loophole. Yeah, but you see, for supersymmetric field theories, you can match the number of microstates. No? They are not free. The charged black holes that you use, for instance, in the Strominger-Waffa entropy formula, for example, they are interacting. They are interacting theories. They are not formed by by condensing a single free scalar. They have a lot of microstates that arise from states from wrapped membranes in the internal cycles of the Calabi-Yau. There is a lot of richness no? Which this theory would not have, no? And like those are not a counterexample, no? Like all symmetries in string theory are gauge symmetries, no? Um, yes. So if at this scale the black hole evaporation stops, okay? So if your black hole starts evaporating and becomes super small, no, at a certain point, quantum gravity would kick in and it will stop evaporating, no longer. If that happens, then you can start forming this macro state of tiny black hole. You just build as many as you want, and you can bring them together and build a huge black hole with a huge area, but with a single macro state because they are not interacting. Okay, and that would contradict this formula. The way out is that there is a scale that you reach before you reach the scale at which gravity kicks in, where your symmetry is broken. No? No? There are symmetry breaking effects. And therefore, the symmetry is no longer there to protect your black hole from radiating. No? And it can evaporate before you reach the Planck size, the Planck scale. Okay? Mm-hmm. Because it's a black hole, no? It's still a black hole. We can take it, maybe we can take it after, no? Let's take it after. It's just an heuristic argument, no? The idea is that it forms a giant macro state, no? And you can make it as big as you wish because you can produce as many tiny black holes as you want, no? And so you want to argue that there is a scale where symmetry breaks before this happens, no? Yes. Mm-hmm. No, there is a single microstate. No, there is no. Yes, there is no. There are not many configurations. There is only one configuration for this system because it's a gas of non-interacting things. No, they don't interact. So so out of this argument, what we argue is that if there are global symmetries, they are emergent. Okay, this is what I wanted you to take home. No, which is this claim. Okay, I agree. This is just a qualitative argument, and like establishing this rigorously is one of the open conjectures about the quantum behavior of gravity, the lack of global symmetries. So I'm not claiming we proved it. I'm just saying this is a heuristic argument to convince ourselves that this should occur, but it's not a convincing proof. No? In particular, like we are working with a single free scalar field. There are many other kinds of charges, and like it requires a lot of effort to argue for it. And luckily for holographic systems, there are arguments to prove it that are more rigorous than this. No. However, the take-home message is that symmetries are emergent. No. Now, out of the fact that symmetries are emergent, we would like to build an inductive argument to show that symmetries must be described to understand what is the structure that can encode symmetries. So we will do it inductively. on the dimension of space-time. And I think I won't have time to complete it because we only have 10 minutes. so I will present the first part of the argument and the second part of the argument. We conclude the argument tomorrow, okay? So in a 1+1 dimensional theory, all excitations are particles, no? And particles have word lines, which are trajectories, which are the trajectories in space-time, no? Now, the physics of these particles is governed by a one-dimensional path integral, no? And if we consider the system at low energy, below the M Planck, such that the gravitational interactions can be neglected, and we end up with a system that will have an effective field theory description, no? No? Now, in particular, we expect to be able to take this limit in such a way that most excitation of the original gravitational system, they just decouple completely, while retaining a smaller collection of excitations that are still interacting among each other. No? So we are essentially flowing. No? We decouple gravity, we recover our symmetries, no? And we are at an intermediate energy scale where we still have a lot of excitations around. So our field theory has an interesting dynamics. No? Now, we want to characterize this excitation using the physics of a corresponding quantum mechanical word line theories. No? Some of them will be gapped and will flow to their ground state at energy below lambda. No? So these word lines, some of them will be gapped and flow to their ground states at energies below lambda. And some other, instead, will retain some dynamics. No? Moreover, these lines can all be organized according to the energy that is required to displace their position in space-time. So, if the energy cost to displace them is 0, then they are topological lines. And otherwise, if the energy cost is infinite, they give rise to some relic, to some defects. No? And if it is finite, then they are excitations of your system. No? So if it is 0, they are topological. If it is infinite, they give rise to defects. And if it is finite, they give rise to the excitations of your quantum field, or say effective field theory description. Now, moreover, we can consider stacking these lines on top of each other. No? These collections of lines will have an interplay. No? They can merge. No? There are processes no? where these lines can merge. No? There are processes when a given line annihilate into another. No? And there are processes where we can take two of these lines and bring them on top of each other and give rise to a Hilbert space, which is their tensor product. No? No? So all these processes are familiar processes in the physics of particles. No, this is an annihilation. You can also have a creation. No? Out of the vacuum. And there is always a trivial line, no? A line which is empty, that costs nothing to displace, like an empty line. No? So this empty line will give rise to the identity topological defect. No? It's a line that costs nothing to move around. The fact that we can take two topological lines and stack them on top of each other give our collection of topological lines a product operation. No? It's called a fusion product. The fact that our particles can annihilate or be created give rise to maps from the tensor product of D with its opposite into the identity, and vice versa. This is a map from the identity into the tensor product of D with its opposite. Because these are all topological now, so having them at this distance or at a different distance or stacked one on top of the other is the same. Okay? And so, out of this we see, so the structure of these lines, the objects, if you like, of this symmetry category will be these topological lines. Then we have a fusion product, and this fusion product will have these operations, and these operations happen to be called evaluation and co-evaluation in the theory of fusion categories. The fusion operation, in particular, no, because of the topological nature of these lines, will have to satisfy interesting associativity properties. So you can think, for instance, of taking these lines together in a given order. Or in another, say, like this. And you see that the way in which we get to this product or this one might differ. No? So this fusion product that we get on our topological lines is not necessarily an associative product. No? Is this, if we take these two and then we merge the third one or not? That's a feature that we want to be able to compute. How to compute it? You see, these are all topological lines, so we can decide to take this diagram and glue it to the one on the bottom. to measure this lack of associativity. You see here we have D2 and D3 coming together with D1, and here we have D1 and D2 coming together and then joining D3 in the two opposite order. And if this bubble evaluates to something non-trivial, then we can measure how much the fusion product that we have fails to be associative. Yes? They are different lines. Distinguished lines, yes. Like, it's still an heuristic argument, no? We are saying, no? Assume that there is this scale. Consider the case of two dimensions. Two dimensions, you have only particles. Particles give rise to one-dimensional path integrals, no? As long as you decouple gravity, these path integrals, some of them can become topological, some of them can still become dynamical, other can become defects, other can require infinite energy to be displaced, no? And in particular, the topological ones, since they require no energy to be displaced, we can consider bringing them on top of each other. And when we take two quantum mechanical systems and that are not interacting and we bring them together, we obtain a tensor product of the two quantum mechanical systems that govern them. No? So this is how you can heuristically argue that you will have a category that has a fusion product out of these topological lines. And this fusion product will have an evaluation and a coevaluation out of the creation and annihilation of particles. No? And it will have interesting associativity properties. No? So now I see that I'm out of time and we are tired. But so tomorrow we will finish this argument. But the message is essentially that just out of the idea that symmetries are emergent, no, we can start arguing that the topological lines must have some structure, no, and that this structure organizes quite nicely, and slowly we can fit it into the axiom scheme of a higher category. Okay? Yes. Yes, yes, yes. Yeah, this is just an heuristic argument, no? Just to say that if you assume that your symmetries must be emergent, then they will have an interesting structure, no? Yes. Not a field theory. Not a field theory. We can discuss that. But in quantum mechanics, you only have points. You don't have much to insert, no? We continue tomorrow.